We see patterns everywhere, right? But how do you go from just a hunch, a gut feeling, to actually proving something statistically? Well, that's what we're going to do today. We're opening up the statistician's toolkit to find out how it's really done.
So, let's just jump right in with a classic one. Do taller people actually earn more money? I mean, it kind of feels like it could be true, right? But how do we know for sure? How do we tell if that's a real measurable pattern or just, something we think we see? This is the exact kind of puzzle that statisticians live for. And here's the secret. Finding those real patterns, it's all about using the right tools. Think about it like a carpenter. You wouldn't use a sledgehammer to put in a tiny little screw, right? Same thing here. To find those meaningful connections and not get fooled by just random noise, you've got to know which tool to pull out of your toolkit and when. So here's the plan for today. We're going to explore what it really means to find patterns by looking at 4 essential tools. We've got Pearson's correlation, point by serial, Spearman's rank, and the chi-square test. And then we'll wrap up with what is honestly the most important skill of all, how to choose the right tool for the job. Okay, let's grab our first tool. This is the big one, probably the most famous one you'll run into, Pearson's correlation. This is your go-to, your workhorse, for when you're trying to see if there's a link between 2 things that you can measure with regular old numbers.
Now, I want you to pay close attention to one word here: linear. This is super important. Pearson's is only looking for one specific kind of pattern, a straight line. It's asking a simple question. As one thing goes up, does the other thing go up or down in a nice, consistent, straight line? That's it. That's the only question it's built to answer.
So to make this real, think about it like this. Is there a straight line connection between, say, the number of classes you skip and your final grade? Probably, right? Or what about the number of kids in a family and the total time everyone spends on chores? See, in both cases, you've got 2 things you can count or measure with numbers. That's a perfect job for Pearson's. So when you run this test, what you get back is just a single number. It's called the correlation coefficient, or just R for short. And this number is always going to be somewhere between -1 and +1. If it's positive, it means when one thing goes up, the other goes up too. If it's negative, when one goes up, the other goes down. And the further that number is from 0, as you can see here, the stronger that connection is.
Okay, listen up, because if you only remember one thing from this entire explainer, make it this. This is the absolute golden rule of statistics. Correlation does not imply causation. Just because 2 things move together, it does not mean one is causing the other. Let's go back to our height and salary thing. They might be connected, for sure, but that doesn't mean getting taller magically causes your boss to give you a raise, right? There could be a million other things going on.
And here's another major watch-out: outliers. An outlier is just one weirdo data point that's way off from everything else. And man, can it mess things up. Just look at this. With that one rogue data point in there, the correlation is strong. But take it out, boom, it jumps to very strong. This is huge. It shows how one single piece of data can totally throw off your results and lead you down the wrong path. Okay, so what if your data isn't 2 sets of numbers? What if one of your variables is just a simple yes or no, an either-or choice? Well, for that, we need to grab a different tool from the box. This one is called the point biserial correlation.
The easiest way to think about this one is that it's kind of like a specialized cousin of Pearson's. It's built for one very specific job: comparing something you can measure, like a test score, with something that falls into one of 2 buckets, like pass or fail. So when would you use this? Let's say you want to know, do students from urban schools get different exam scores than students from rural schools? You've got your continuous variable, the score, and your 2-category variable, urban versus rural. Or what about this? Is there a link between how much money someone makes and whether or not they graduated college? That's income versus a simple yes or no. Both of these are perfect jobs for point biserial. All right, tool number 3. Now we're shifting gears a bit. What happens when your data isn't about exact numbers, but more about the order of things? First place, second place, third place, that kind of ranking. For that, we need something different: Spearman's rank correlation.
And the big fancy keyword for this one is monotonic. I know, it sounds complicated, but it's really not. It just means the relationship is heading in one consistent direction. As one thing goes up, the other thing keeps going up. Or as one goes up, the other keeps going down. It doesn't have to be a perfect straight line, it just can't suddenly turn around and go the other way. And this is why Spearman's is so incredibly useful. Let's be honest, real-world data is almost never perfect. It's messy. This tool is more forgiving. It doesn't demand a perfectly straight line, and it doesn't get confused by the kind of weird data that would completely throw Pearson's off. A great example is blood pressure. Systolic and diastolic readings usually go up and down together, but it's not a perfect line. That's a classic case for Spearman's.
Okay, on to our last tool for today. And this one is a different beast altogether. We're going to stop measuring things and stop ranking things. Instead, we're just going to be counting things in different categories. And for that job, we need the chi-square test.
So, what does chi-square do? It answers a really straightforward question. Are these two categories related? That's it. For example, if you know what someone's favorite season is, does that give you a clue about their favorite type of movie? Or are those two things totally independent? That's what chi-square figures out.
Let's make this crystal clear with a great example. Imagine some researchers want to know if male and female students have different preferences for how they learn. Do they prefer books or learning online? Notice our variables here aren't numbers at all. They're just categories. You're either male or female, and you prefer either books or online.
So here's what they found. Just a simple count of how many students fell into each of those 4 boxes. Now here's the cool part about the chi-square test. It starts by calculating what these numbers would look like if there was absolutely no relationship at all. Just pure random chance. Then, it compares that expected random result to what we actually see here in the real data. And if the difference between what was expected and what really happened is big enough, bam, you found a real connection.
Okay, so we've pulled 4 very different tools out of our toolkit. Each one is designed for a very specific kind of job. And that brings us to the final, and I would argue, the single most important part of all of this.
It all boils down to one thing. You have to know what kind of data you're dealing with before you do anything else. Is it numbers you can measure? Is it a ranked list? Or is it just categories? Because grabbing the wrong tool, that's actually worse than doing nothing. It gives you an answer that looks right, feels right, but is just flat out wrong.
And to make that easier, think of this as your quick reference guide, your cheat sheet. It breaks down every tool we talked about, what it's for, and exactly what kind of data it works with. This is your map for picking the right tool every time. Hey, remember that study about how students like to learn? Let's go back to it for a second. By using the chi-square test, which was the perfect tool for their data, the researchers found something incredible. Male students were over 3 times more likely to prefer learning online. Now that is a powerful, specific insight. And they only found it because they used the right tool.
So there you have it. We've taken a peek inside the statistician's toolkit. And now you have the power to look at the world, especially the news, a little more critically. So the next time you see a headline screaming about a proven link between 2 things, you can stop and ask yourself, wait a minute, what kind of data are they talking about? And did they actually use the right tool for the job?